Today we will discuss about the introduction of the analytical chemistry and actually what is the analytical chemistry and what are the different type of techniques available to perform the fundamental tests in the analytical laboratory. So first of all, if you see the analytical chemistry definition, so it is nothing but the study of separation, identification and quantification of chemical components. Chemical components might be natural or else the synthetic materials. So here I want to explain about the basically it is the study to identify the components exactly. So whenever you will receive a material from the process lab or maybe from outside of your industry to analyze that material, so we have to perform the different type of techniques. So by the different type of techniques, we will estimate the quantity or quality, means whether the component whatever we are received is exactly similarly what we are expecting or not. That is the qualitative test. Quantitative means how much content it is there in that material, like anything, like water content means how much water is present in that material. That is the one of the quantitative analysis. Loss and drying means how much loss on drying means when the compound is dried under certain temperature, certain period, up to certain period. So how much the material will be evaporate from that compound. So that is nothing but the loss on drying. So these type of techniques are involved basically in the analytical chemistry. So if you see the table in this slide, the chemical analysis is a process that provides the chemical or the physical information about the consistence in the sample. So basically, these are divided into the two types, like qualitative analysis and the quantitative analysis. As I explained, qualitative means what is present in that material. Quantitative means how much is present in that material. So in the qualitative analysis, gives an indication to identify the chemical species in the sample, and in the quantitative analysis determines how much amount of the present in the sample. So here, just I want to add one more point about that. During the manufacturing of active pharmaceutical ingredients, both these qualitative and the quantitative tests are very much important for all type of materials. As I explained in my previous presentation, those are different type of materials are available in the API pharmaceutical industry, like raw materials, intermediates, final products, final drug substances, etc. So in all these components, we have to analyze these two types of analysis. Like qualitatively, we will do some tests, and then quantitatively, some of the tests we have to analyze. I hope everybody is understood what is the analytical chemistry and what type of analysis we will do basically. So in the coming slides, I will update and I will perform and I will do a separate presentation on the qualitative and the quantitative analysis. But in this video right now, I am just explaining about what are the different type of techniques involved for the analysis of a particular component. So going to the next slide, the analytical methods are divided into the two types. Basically, it is the classical methods and the instrumental methods. So some of the methods, by using the simple chemicals we have to perform, like only the chemicals and just oven, drying, etc. We will use in that analysis. But in some analysis we have to definitely use the some type of the instruments. So in the classical methods are especially we can call as the wet chemistry methods. Wet chemistry methods involve in the test like precipitation tests, extraction tests, qualitative tests, qualitative analysis by identifying the color and the odor, and some type of test like a loss on drying, residue on ignition, and gravimetric analysis, identification of the chemical species present in the material, So those are all called as the qualitative methods. So these qualitative methods, uh, in the wet chemical methods, again we have the both qualitative and the quantitative. So whatever I explained, like description, solubility, identification, and these LOD, ROA, heavy metal, these are all called as the qualitative wet methods. So in the wet chemistry, again we will have the quantitative techniques also. So in the quantitative techniques, what we will measure, like weight or value. So how much weight it is gained or decreased. So this is the quantity we will measure, and volume. So sometimes we will do the volumetric analysis like titrations and some chemical solubilities, etc. So those are the quantitative analysis. So coming to the instrumental methods, the methods like spectroscopy. Spectroscopy is the a separate branch of the analytical chemistry where we will use the spectral studies like FTIR, UV, and NMR, MAS. So these are all the spectroscopy methods. There we will use the particular range of the radiation, UV radiation and IR radiation, and some means the frequency whatever we will use, those are the different ranges. So based on the different region of that frequency, we will get the different pattern of the materials. Those patterns are unique for the different products. Like example, if you take the FTIR, so in the FTIR we have a separate wave numbers assigned to identify the separate functional groups. So when you run a IR spectrogram, IR spectroscopy, if you see the spectra of that particular chemical compound, you have a unique wave numbers. Like if you a band coming around the 1650, it is equal to a presence of a carbonyl compound in that compound. So if any band is observed around the 1100 and the 1200, so those are the carbon stretchings, carbon carbon CC stretchings. So CH stretchings also will be present around the 1300, 1200, like that. So in that region, whatever the bands are observed, those bands we will compare with the structure of your chemical compound. So based on that, we will identify. And whenever we will analyze the FTIR, first we will run the standard material spectrogram, and also we will run the sample, whatever the test sample spectrogram also we will run. So we will compare the both standard spectra versus sample spectra, and we will see the correlation of that particular spectra. So based on the correlation, like always it should be close to the 1.0, but based on the limitations of the handling and the pellet making, the instrumental errors, so generally it should be more than 0.95 for the key starting materials and the intermediates. And when it is coming to the API or the drug substance, it should be very close to the 1, like 0.99. It should be close to 0.99, like that. So, and again in the spectroscopy, one more technique is that UV spectra. So basically, when we will use the UV spectra, we have to identify the spectral maxima, UV maxima of that particular compound. So where it is having the UV maxima, then we have to run a UV run and compare with the standard again with the sample. And sometimes we have to quantification test also we will perform by the UV, like cleaning methods, especially in the industry, in the API division, for the cleaning methods, equipment cleaning methods. So we will generate a method to identify in the cleaning solvent whether the material is present or absent. So to that we will develop a method by using the UV technique. So in that what we will do, generally the limit of the KSMs and intermediates, we will use a vessel in the process or manufacturing area. So after using of that material, so we have to clean that vessel or reactor. So how we will confirm whether it is completely cleaned or not? So for that we have some of the guidelines like APIC guidelines. So according to that APIC guidelines, the KSM or the intermediate, we have to show the cleaning till 100 ppm like that based on the calculations. So once we clean that vessel, so the cleaning solvent should contain not more than 100 ppm. So by that we will ensure the vessel is completely cleaned or not. So for that we will first prepare a standard solution of 100 ppm and we will run in the UV. So we will get a UV maxima with a specific absorbance at particular nanometer. So again after cleaning the vessel we will get that cleaning solvent. That cleaning solvent we will basically it is a cleaning sample, and that sample we will scan by UV, and we will also take the reading UV reading for that sample. So how we will confirm that the absorbance in the cleaning sample at that particular nanometer should be less than our standard absorbance. So if it is not, again we will inform the same thing to the manufacturing people, and they will one more time they will clean by using the cleaning solvent, and again we will do the analysis, and by that way we will confirm whether the vessel is completely cleaned or not. So that is one more technique of the spectroscopy. And the coming most advanced spectrography techniques are like HPLC. HPLC is also the detection part is again based on the spectrography technique only, particular to the UV detector. And the next technique is the NMR. NMR is the completely nuclear magnetic resonance, that is a spectroscopy technique. And the mass spectroscopy, that is also based on the mass identification of the your main compound as well as the impurities, and the fragmentation of the impurities, that everything we will do. So next is the electrochemistry. Electrochemistry is nothing but the quantification of the species by differentiate the potentials, current between the components, and the voltammetry, and those are all coming to the electrochemistry. Even the electrocapillophoresis is also one of the electrochemistry only. And the next techniques is the chromatography. So basic analysis in the ABI industry is the to identify the impurities by the separation techniques like HPLC and the GC. So these are all the these are both the two very strong techniques by using the instrumental methods. In the both way, in the qualitative test and the quantification test, we will use in the more of these two instruments. And again, the as I said, the mass spectroscopy and NMR spectroscopy are the used for the structural elucidation basically. And XRD also one of the instrument, and a lot of instruments are there. As I told in the previous this presentation, we have a different type of instruments in the API. So as I done a short video on the what are the type of different instruments available in the API. So in that almost we have covered around 33 to 36 instruments. So all the instruments I covered, you can refer that small video. So what are the different instruments we can handle in the analytical lab. So going to the next slide, what is the wet chemistry basically? So wet chemistry is a term used to refer the chemistry generally done in the liquid phase. So it is also known as the bench chemistry because many of the tests performed are done at the lab bench. Because here in the wet chemistry, mostly we will not use the instruments. So basic equipment like glassware, pipettes, burettes, or maybe some measuring cylinders, and test tubes, volumetric flask. Only these are the instruments or equipments I can say a glassware, basic glassware we will use, and we will identify, and we will basic laboratory test. What we will do is the wet chemistry. So wet chemical analysis excludes the techniques. Like I said, we will not use the instrumentation for the quantitative analysis, etc. There are two procedures which are normally used to perform the wet chemistry. First is the titrometry, which involves the volume measurement for the liquid of the reactant or sample, whichever we will perform the analysis. And second is the gravimetry technique, in which we will use the technique to determine the weight of that compound. Either the product weight we will monitor, or the compound, after analysis we will take the weight of that compound. By that we will determine particular quality or the quantity of that character of that material. So when we will discuss about the quantitative analysis, basically we will monitor only the two things, either by value or by weight. So wet chemistry techniques can be qualitatively, chemically measurements we will done sometimes of color changes, like calorimetric determinations. So where we will see the distinguish the tests, limit tests, or the identification test by checking the color of that substances, or maybe the formation of that compound by using the different type of reagents. So if you see the identification of the halogen test, like chloride test or the bromide test, so the if any compound is having the chloride in that compound, we will perform one test, and at the end of that test we will get a white color precipitate. So if that white color precipitate is present in that material, means uh, detected in that material, means the chloride is present, like that. That is one of the example. So in the zinc or the arsenic, or maybe in the transition elements which are present in that material, to identify that material also, we will perform some of the color identification tests, because the transition elements having the colors when it is changes from one state to another state. Like if you see ferrous, it is having in the Fe plus 2, it is having one color. At the same time, Fe plus 3 is having one more color, other color. So this is the simple character we will use to identify whether the material is meeting our requirements or not. So going to the next slide, what are the different topics or the different analysis will cover under the wet chemistry. So we will discuss one by one. In this video, we will discuss still determination of the inorganic by RO and heavy metals only. The titration and the other things we will discuss in another next video. So in the first this video, we will discuss about the water content determination technique, like Carl Fisher titration and the coulometric titration, and the Lawson drying, melting range. These are the tests we will discuss. The titration and other things I will briefly explain in this, but the detailed thing we will discuss in the next video. So again, these are some of the list of the wet chemical procedures, description, appearance. If you see the initial slide, these are the techniques basically we will use to the qualitatively and the quantitative. Like in water content, we will determine the water content present in that material, either it is in the KSM or intermediate or the API. And this water content can be determined basically by the two techniques, like KF titration, this is the titrometry, and the coulometry. The determinations, the principle in these two determinations are different. However, the final aim of these two tests are same, to determine the water content only. Class and drying is nothing but how much solvent is there, either it is only the water or the combination of water plus other solvents. So whenever you are preparing your compound in the manufacturing process or in the route of synthesis, we will use a lot of different type of organic solvents like IPA, methanol, THF, ethyl acetate, hexanes, etc. So if you want to in the process of that final compound preparation, the compound will be dried at a particular temperature in the manufacturing area. So after drying, to unload that material, whether the all solvents are evaporate properly or not, completely evaporated or not. So to check that one, we will perform this analysis, loss and drying. So wantedly we will heat that material. So initially we will take some weight, and after heating also we will take weight. The difference we will establish as the amount of the solvents in that presented in that material. So why we have to do the moisture content or the LOD? Basically, if you want to sell your compound in any region, so there is a guidelines, or the monograph means the specification is already fixed for that API, or some of the compounds already monographs are available in that particular region. So if you want to sell your compound, you have to meet that pharmacopoeial monograph or pharmacopoeial specification. Like if you want to sell your compound in the US, you have to meet the USP monograph. So in that monograph, they fixed the specification. For example, the water content in your API should not be more than 0.5%. So your API should not be more than 0.5% means after analysis of your compound, the water content, the water should be below 0.5%. In the same way, loss and drying also you have to analyze as per the given conditions in that monograph. Like what are the conditions for the LOD means at what temperature and how much duration we have to heat that compound, like 105 degrees under vacuum for 3 hours. So in that same conditions, you have to heat that material, and by maintaining the proper conditions, like you have to take the weight in the calibrated balance. So that, and after weighing, you have to keep the bottle, LOD bottle, in a desiccator to uh, to observe, to not observe the moisture available in the atmosphere. So in the desiccator you have to properly maintain with the desiccant, so it should not be allow the outside moisture. So all that precaution, under precautions, you have to measure the LOD in that compound. So particularly he will provide the, in the monograph they will provide how much compound also you have to take for the LOD. Sometimes you have to take 1 gram, or sometimes you have to take 2 grams or 3 grams or 4 5 etc. So generally we will take 1 gram, but based on the specification of the compound, if the specification of the compound is very stringent or very low, like not more than 0.1%, at that time we will take some more quantity, like 5 grams we will take. But as per the general practice, general chapter of the LOD USP chapter, whatever the material you will take, whatever the quantity you will take, it should be in the height of the 5 to 10 mm only. When you filled the material in the LOD bottle, it should not be cross about 10 mm height. Why? Because if the thickness is more, whatever the heat you are giving to that compound by keeping that LOD bottle in the oven, that should not be penetrate inside. So whatever the solvents or the whatever the vapor present in the material should not be come out properly. So to come out properly from that material, it should not be more than 10 mm thickness. So that is the minimum requirement of any LOD test. So in that way we will calculate or we will perform the loss on drying. And the next is the melting point or melting range. So why we will require to analyze the compound to know the melting range? So it is a identification test, a fundamental identification test, whether your compound is exactly following the theoretical point or not. Means at the prescribed melting point, prescribed heat only it is taking or not. Why? Because based on the structure of your compound, based on the polymorph of your compound, based on the crystal arrangements of your compound, the melting point will be changed. So whenever you are identify some of your standard compound is having some melting point, say around 150 degree centigrade, your sample also have the, it should have the same melting point at 150 degrees only. Then only your identification will be pass. Okay, that is the characteristic identification of your compound. And coming to the next topic, inorganic materials through ROA. ROA means it a residue on ignition and the heavy metals. So why we have to determine the inorganic materials? So as I said, in the processing or the manufacturing processing of the material along with the solvents, those we will determine by using LOD and water content. So the inorganic materials like sodium salts, potassium salts, or maybe all the inorganic solvents like bromine, chlorides, halides. So these are all the alkali materials. So these are all the inorganic salts which will not evaporate at higher centigrades. So the carbon material is whatever the material we will synthesize, it is nothing but 99% is the carbon material. COHSNS. So these are all the carbon carbohydrate compound. It is having the only elements like carbon, oxygen, hydrogen, sulfur, nitrogen, etc. These are the organic moieties will evaporate at particular temperature, not more than maximum at 800 degrees. The organic material will be melt and evaporate. But the inorganic materials like sodium, chloride, potassium, all these materials will not evaporate. Even because the melting point or the boiling point of these heavy metals are very high. So that's why the component should have the very limited amount of the inorganic materials. So again, the as per the pharmacopoeial standards in the API, we should not have more than 0.1% of the residue on ignition. And coming to the heavy metals, there is a separate chapter available in the ICH, that is the ICH Q3D, elemental impurity analysis by the ICP-MS or the ICP-OES, etc. So coming to the ROI, it is the limit of the 0.1%. So in the ROI, we will know the combined quantity of the heavy metals or the inorganic materials. But in the heavy metal test, we will know individual element. Sorry. So what is the sodium is present, what is the potassium is present, what is the aluminum quantity is present. So in the ICH limit, we have quantified the elements according to the different classes, like class 1, class 1A, class 2, class 2A, class 3, and other elements. So with a different limits, like class 1 solvents is class 1 solvent has the 7 elements. So those are having the different limits like 0.1 ppm, zero point 0.5 ppm, zero point 0.2 ppm, or 5 ppm, etc. So I will explain in another video about the ICHQ3D general chapter. So in that I will detail about the limits and etc. So if you will take the compound based on the intake also. Like if the compound is a parental, oral, or maybe applicable. So based on the intake of the material also, the limits will be changed. If a material is taking by orally, so the limits of that metals will be different. If we take that material through injection, so the limits will be different. Okay, so by the ICP-MS and the AAS we will determine the heavy metals, individual heavy metals. And next is the titrimetry. So anyway, I will explain in the next video about the titrimetry. So in the other wet chemistry topics involves like description or the appearance. This is nothing but whether your compound is the solid or the liquid, with what color range, like whether it is the white material or green material. So whatever the color your standard is there, it should match with your sample also. The pH, the final pH. Why? Because the whenever we are taking the material at particular pH only, it will go under the different kinetic studies inside your body. So because of that, the compound pH maintenance is very important. So this is the very crucial parameter for the API. And the solubility or the miscibility also. If the compound is the solid, we can call as the solubility, and if it is the liquid, we can call it as the miscibility. And the appearance of the color of the solution, sometimes we have to do some color of the API by dissolving in particular solvent, and that color should be matched with your standard color, like that. And the specific gravity, that is nothing but density, bulk density and tap density. So the why it is we require the bulk density or the tap density, because whenever you are packing your material, or whenever you are making some capsule, so by loading that your API, you should know the density of that particular API. So when it is simple density means, suppose if you take the material around 100 gram and pour into the 250 measuring cylinder, how much occupancy it is taking, whether it is completely filled in the 250 or only the 100 grams 100 ml it is occupied. So based on that we will know the bulk density. The tap means after pouring your material we will do some taps. So in a separate video I will explain about again. So what is the tap density? So the tap means we will do the particular taps like around 250 taps, 15 taps, 20 taps, like that. So after tapping we will measure the density. That is nothing but the tap density. And the non-volatile matter, this is particularly we will measure in the solvents. So whenever we will take any recovery solvent, so in that recovery solvent, after heating that solvent, how much material is remaining in that solvent, that is the non-volatile matter. And the insoluble matter is the same thing. And hygroscopic study, so the hygroscopic study is nothing but fundamental study to know about the uh, water absorbing or moisture absorbing nature of your particular compound. So to this one, we will expose the material at a very high humidity. We will keep the material in a desiccator where the desiccator is filled, or the base of the desiccator will be filled by the a material, a solution which gives the 90% humidity of the desiccator, like potassium chloride, ammonium hydroxide, ammonium chlorate, and the potassium sulfate. Potassium sulfate is the highest moisture given solvent, where it can be reach up to 97% also. So in that atmosphere, closed atmosphere, in the desiccator, we will keep our material in a petri dish by in the opening or in an open petri dish, and we will expose that material up to 24 hours. So if your compound is having a nature to absorb the moisture, so the weight will be changed. So initially we will take before keeping that material in the desiccator, and after 24 hours also we will take the weight of that material, and we will compare the weights, and we will calculate by the initial weight and after weight. So why we require this hygroscopic means, whenever you are transporting your compound from one area to another area, because in the worldwide regions are divided based on the temperature and the humidity. In India, if you are In India also, in some area the humidity is the around 40% or the 50% only. But in certain regions like coastal regions, the humidity will be very high, around 70-80% also. So you are exposing, or when we are taking the material outside in one region, it is absorbed and the quality will be vanish, or quality of your material will be altered. So if you know that material already as a hygroscopic material, so you will take care by a different package, different packaging condition. Like that, you will triple laminated pack, or you will LDP pack under triple laminated pack under a nitrogen atmosphere with a closed sealing HDPE drum. Like that, you will pack the material in such a condition that like that it should not absorb the material. So if your compound is not a hygroscopic material, so those are all packing conditions are not required. Simply you will pack in a LDPE condition and directly in a HDPE drum, or maybe in a triple laminated pack. So there the nitrogen purging is not required. So this is the characteristic property to know whether what type of packaging or what type of the export conditions you have to maintain while shipment procedure when you're done for your compound. So next is the identification test. These are the simple identification tests based on your compound nature and the compound structure. So whether it is having a salt, or whether it is a base, or it is having any heavy metals, or it is having a particular salt like sodium, potassium, or these are all the tests coming under the identification. And sometimes the functional group identification like by FTIR, MOS, NMR, those are all also coming under the identification test. So next is the very important topic is the physico-chemical properties. So these are basically required to filing purpose, and to know to develop some of the methods also. Physico-chemical properties includes about the what is the characteristic properties like solubilities, and the hygroscopicity, and the melting points, and the log pH values, log D values, and the separation techniques like saturated solubility means how much, at what temperature it is, in what type of buffers, and what type of solvents it is, solubility is more, like that. And the XRD polymorphic structures, whether it is a crystal, it is having in the crystal form or a amorphous form, and whether it is having a thermogram or DSC, TGA. So those are all coming into a physicochemical properties. These are basically a filing requirement required by all the regulatory agencies when your compound is filing to the different pharmacopoeia or the regulatory agencies. So I will do a particular separate video on the pharmaceutical requirement for the physicochemical properties also. So if you are going to the next slide, it is the water content by Carl-Fisher titration. So this is the very fundamental technique used in the any pharmaceutical laboratory. If you take the API, or if you take the drug substances or drug product formulations, anywhere, the fundamental technique it is the water content analysis. So if you see the history of this KF titration, it is a classical titration technique, and it is actually invented by a German scientist named after Carl Fischer in the 1935. So basically the main ingredients of the Carl Fischer reagent is the iodine, sulfur dioxide, and imidazole buffer, and the solvent is the methanol. So if you want to perform the KF titration, you need a reagent, that is the Carl Fischer reagent. So this reagent consists of all these four ingredients like iodine, sulfur dioxide, imidazole, and the main base solvent is the methanol. So what is the principle involved in the water content? It is a very fundamental principle. So I will go through the principle one by one. After I will give the explanation. So the principle includes like this: the 1 mole of iodine is consumed for each mole of water. So this is the base why and how it will detect the water content. So whenever a molecule is present in your water molecule is present in your compound, that is equal to 1 mole of water. So the titration reaction proceeds till the total water content in the sample is consumed and the end point is determined electrometrically. So here the voltage difference between the two electrodes will be measured. The KF titration is a voltammetric titration, amperometric titration. Amperometry means the current. So the because of the iodine is transferred between the two electrodes. It is a biamperometric titration. Actually, the whatever the electrode we will use in the KF titration, it is the biamperometric. Means two electrodes we will use as a combination of the two electrodes. The biamperometric titration will be run. In that, between the voltage between the two electrodes will be measured. Whenever there is a water molecules are available, so the ratio of the iodine between the two electrodes will be fluctuated because the water content will be reacted by the iodine. So whenever this iodine will consumes, the potential difference, current difference will be present in the between the two electrodes. So how that amount of the water content is directly proportional to the current, and the current is directly proportional to the iodine. So in that way it will measure. It is a simple fundamental technique and simple fundamental principle. So here it is written like that: the end point of the reaction is determined electromagnetically using dead stop procedure. Dead stop procedure is nothing but when always the potential difference between the two electrodes should be zero, always. So to when the compound or when the titration solution is presenting some water, the iodine will be consumed. So once the iodine is consumed means there is no equal between the two electrodes. So to make the volume stop, it will consume again the current will be passed between the two electrodes. That is the dead stop procedure. Sorry. So if small electromagnetic force is applied or electromagnetic field is applied across two platinum electrodes immersed in the reaction mixture, a current will flow as long as free iodine is present. Yes, understood as I explained before. To remove the hydrogen and depolarize the cathode. That means to neutralize the water. So when the last traces of the iodine has reacted, the current will decrease to zero. So that means the complete iodine will be consumed. That means the complete water content will be completed in that solution. Then it is decreased to zero and become close to zero. There the titration will be ended. So the method is confined to those cases where the test substance does not react with any component of the reagent or with the hydrogen iodide formed during the reaction with water. The following compounds interfere in the coefficient. It means the third point is that so whenever you are taking any compound or the media, so that should not be react with your compound. It is right now. So suppose if your compound is directly reacting with your Carl-Fisher reagent, so there is no value or uh, there is no point to detect the water content. because the actual water content will not remain same. Sometimes the compound itself, by reacting with your reagent, it will produce the water, extra water it will produce. So suppose it is 0.5% is there, because of the chemical reaction it will release one more percent. So wantedly, because of the reaction media and the nature of your compound, it is deliberately releasing the higher content. So to avoid that one, we have to very caution to identify the solvent and in which media we have to determine the water content. It is very much important. So if you see the components of the Carl-Fisher reagents, with the oxidizing agents such as the chromates, dichromates, and copper, iron salts, the higher oxidase and the peroxide. So the manganese, so, so the manganese dioxide plus your any compound having the primary amine, so and it will react with the iodine. So if you see this reaction, it is deliberately releasing the 2 moles of water content. So whatever the water present in that compound, primary amine compound, along with that, because of this side reaction, again the extra water also will react. It will give the erroneous or the wrong result. Like that, you can see the zinc oxide when it is present in the primary amines. When it is present in the zinc oxide, also it is releasing some water moiety. And the sodium bicarbonates, when it is present in the primary amines, again it is releasing some water content. So these compounds, when presence of these salts, it is not suitable to perform this water content. So the next example is the ketones or the aldehydes. So the ketones and the aldehydes, when reacting with the water methanol, because the primary solvent, what we say is the methanol is the base for the KF reagent. So in this methanol, the ketones and the aldehydes will react, and it will form the ether as well as the water content by additional product. So this extra water will be reacted, and again the aldehydes and the ketones from the bisulfite products also, uh, it will produce the water content. So these are the additional solvents, and some of the solvents we have to avoid when performing the particular compounds. So basically the methanol is the first solvent. We will use the general solvent for the KF, and a mixture of the methanol and the pyridine, and purely pyridine. Pyridine is especially we will use for the analysis of the ketones and the aldehydes. Why? Because if it is not produce the water. When the aldehydes and the ketones are in the presence of the methanol only, they will produce the water. But in the presence of the pyridine, it is not having the any reaction, and it is not produce the any water content, extra water content. And the others, but nowadays most of the quality control labs, they are avoiding the pyridine also because of the some health hazardous issues. So in place of the pyridine, number of the other solvents like DMF we can use, and imidazole we can use. So in the methanol, we will add wantonly some of the amount of imidazole. So and that imidazole will act as a weak base, and it will produce the and it will participate in the reaction. And we can use a combination of the methanol and the esteraldehyde, and methanol plus chloroform, and methanol with glycol, ethylene glycol, and that also we can do. These are all some of the additional the other solvents we can use in place of pyridine. So oven technique can be used to avoid the side reactions in the water content determinations. So this oven module can be connected to the Carl-Fisher and coulometry. So if you want to avoid a solvent titration, so directly there is a technique present in the coulometry, that is the thermoprep technique. We can call as the oven thermoprep. Means there we will fill the some small vial around 5 to 10 ml vial, that we will fill with the compound, and that compound will be heated at a particular temperature around 100 degree and 105 degree. So there the water will be directly evaporated. That evaporated water will be pierced into the titration vessel. So basically you are not adding the compound in the titration vessel, but only amount of the water present in the compound will be transferred into the titration vessel. For that you have to heat the material to generate the water vapor. Okay, that is one of the advantage of the coulometry. So the required sample quantities for a coefficient titration. So as per the USP, there is a guideline is there. The compound should be present around 2 to 250 mg of the water. Means when we are taking the compound based on the specification or based on the content of the water, minimum it should be contain 2 mg and maximum it should not be more than 250 mg in your sample. That we will decide based on the specification as well as the amount of your compound or amount of the sample you are taking for the titration. So you can see, suppose for example, the specification limit is the 0.1%. The sample we have to take around 5 grams. So if the compound is having around 0.1%, in that 5 grams, you have the 5 mg of the water. So that is the requirement. Like that, if it is the specification limit is the 0.5, you have to take 1 gram, because from zero point 0.1 to zero point 0.5 it is increased 5 times, so the quantity you can decrease 5 times, 5 to 1 again, but the amount of the water will be remain same. So like that, this table will explain you about how much quantity you have to take to determine the water content. So the next advanced technique to determine the water content is the coulometry. So the basic fundamental modification done in the coulometry from the Carl Fisher is that uh, the alcohol base solution containing the sulfur dioxide and a soluble iodine. So here there is no iodine present in the reagent solution. So basically in the electrode itself, the iodide will be present, soluble iodide. Upon electrolysis, iodine is liberated at the anode. The endpoint is detected by the four electrodes by a pair of electrodes which function as a biamperometric detection system and indicate the free of iodine. So when all the water has been consumed, the excess of iodine occurs, which usually is detected electrometrically, thus indicating the endpoint. So here in the reaction solvent, the iodine is not present. Basically, the sulfur dioxide and a soluble iodide is present. So based on the same, the technique will be same here and there, but it is the Carl Fisher reagent is not available or maybe not required in this coulometric titration. So for the coulometric titration also, as per the USP, it is the requirement is the 0.5 to 5 mg, because the coulometric technique is the very sensitive than Carl Fisher. In Carl Fisher, the amount and the material requirement is around 2 to 250 mg. But whereas in the coulometry, the requirement is only 0.5 to 5 mg sufficient, because here the sensitivity is very high for the coulometry, because here there is no iodine is directly involving in the reaction. Because of the electrodes only, the iodide electrodes will be present in the electrodes itself. That iodine will be discharged. So based on the movement of that iodine between the two electrodes, it is the very high sensitive electrodes. That's why very small amount also it will detect very easily. So coming to the next topic is the loss and drying. As I explained earlier, loss and drying is the technique to detect the uh, solvents and the water content by a specified temperature. So different pharmacopoeias can be give the different conditions like at what temperature and how much duration we have to heat the compound, and what is the desiccator you have to use, like sometimes they will mention the phosphorus pentoxide, sometimes they will use the silica gel, etc. So the product isolated from the solvent or the water is required. This test can be only used for the class 3 solvents like low melting salt. uh, Low melting salts, all solvents loss cannot be determined, because whenever the compound is having a very low melting point like less than 60 degrees or less than 40 degrees, this technique is not useful, because to evaporate your solvents minimum, based on the boiling point of that solvent, maybe it is required like more than 40. If the lowest melting point like boiling point like methanol or the highly volatile materials, it is more than 30 or 40 only. If your compound is having a water is also available in that compound, you have to definitely heat till the 105 degrees. So but because of the low melting nature of that compound, the actual solvent will not be determined. So that is the limitation in the LOD. So that the limitation will be uh, the drawback and the limitation will be addressed by the next technique like thermogravimetric analysis. That is nothing but the TGA. So in the TGA, so it is a again a different technique. It is not exactly comes under the wet analysis, but it is a thermogravimetric analysis, means it is the thermal technique where we will take the compound in a small pan, and the heat is take that material, and it will detect the loss where exactly it is happen. If you see the thermogram of a TGA, so the in x-axis you have the temperature, and in y-axis you will have the weight loss. So by slowly observing the temperature, the compound, if it is having a very volatile compound, the weight of that compound will be decrease. So we will monitor the weight decrease at particular temperature and weight of the initial also. So based on that calculation, we will know what is the amount of the vaporized solvents are present in the compound. So this is the TGA is the characteristic property. It can be used to know the structural property of that particular compound also, and we can determine the weight loss or gain due to the decomposition, oxidations, dehydrations. So the elucidation of the compound will be very useful by using this technique. So as I said, the melting range also very important identification test. Temperature range which is sample it's melt from the solid state to the liquid state, it is called as the melting range. And most crystalline compounds actually melt over a range of few degrees or less. So acceptable criteria is the 2 to 5 degrees. Means suppose the theoretical melting point of a particular compound is the 140 degrees, means it can be up to plus or minus 5 degrees, 135 to 145 is allowable. So the if the compound is having a different range of that theoretical range, means it is having some of the impurities. Because of presence of that impurities, the melting point or the melting range will be differed. Either it will be melt early, or either it will be melt, or it will be melt in later temperatures. The pure compound is there, and 100% purity means it will melt at that particular temperature or the specified temperature only. Melting range can be performed by using the instrument like oil bath, that is the manual melting point like Coleman, or an instrument containing the heating block, that is another apparatus like Optimum. These are the two companies, Coleman and Optimum. So Coleman is the basic technique. You will use the oil bath where the temperature will slowly increase, and at that particular temperature the compound will be melt. Where in the optimal, in that we will use the heating block where there is no oil bath. So if you see the next slide, it is the picture of the optimal instrument where we have the digital notation to identify the temperature, and the next figure is that if you see the three capillaries at the same time, we can monitor the melting point of the three compounds at the same time. Okay, so I think we reached the final two slides. So the slide is number 17 is determined about the inorganic and heavy metals. So the why we have to measure the inorganic means, as I said, in the ROS or the process chemistry, we will use the different type of the reagents or the buffers or the salts. So based on those compounds, the compound will contain the inorganic materials. So generally the requirement is, as per the pharmacopoeias, the ROA should not be more than 0.1%. So by using this technique, ROA, we in this technique basically we will heat the compound at higher temperatures like 600 and 800. So all your organic compound will be evaporate. Only the inorganic salts, whatever remains in the compound, will be present. So that material only we will measure. So to conduct this experiment, we have the different vessels like platinum, crucible, and silica, because these are the materials having a different higher temperature melting points. So that's why those compounds are not melt whenever you are keeping in the muffin furnace along with the compound. Basically, the platinum is the crude, pure material. It can be having a very high temperature of melting point like 7,000 or 6,000 like that. So, but we will use only the 18 degrees centigrade. And if we keep any containers like general materials, those will be melt at these temperatures. So because of that only, we will keep the silica crucibles, glass crucibles, silica crucibles, platinum crucibles. So to conduct this experiment, the test is usually determining the content of the inorganic impurities present in the sample. And heavy metals are, as I discussed, we can determine only by AS and the ICP-MS test. This is the separate video I can do to explain the what are the requirements about the ICH, what is the ICH Q3D, and what are the different classes of the elements, and what is the fishbone diagram, and what is our how we have to identify the metals present in the compound, and everything I will explain in that separate video. So if you see the list of the inorganic materials, the heavy metals like lead, mercury, bismuth, antimony, arsenic, cadmium, silver, copper, mandolin, platinum, palladium, etc. Those are the heavy metals test we will do. And the metals like lead, heavy mercury, bismuth. So this will come in the sulfated ash also. Sodium, potassium will also come into this picture. So individual metal ions, this can be identified by the ICP-AS and higher ICP OES test like that. So these are the type of the inorganic impurities we just presented in one table. So I just came to the end of this slide. So thank you very much for your support. So please go through the slides and understand your requirements and the basic. This is the very basic fundamental presentation. I explained about what are the different wet chemistry techniques present in the lab analytical lab, and what is the purpose to perform these tests, I explained. So if you have any doubts, please raise in the handle box. Definitely, I will try to answer your questions. Thank you very much, and hope you meet in the next video. I will do the second part of this video. In that, we will explain about the titrations and other physicochemical properties, etc. Thank you very much. Ashok, Ashok, ఏంటిరా ఏం పోకమాన్ కార్డ్స్ అందులో పెట్టినావు నువ్వు